This is lecture 2 for chapter 3 in ODE, and I'm going to work through an example of a nonlinear system with a periodic orbit. In these examples that I'm doing, I'm trying to hit all of the classic examples of nonlinear systems. In the previous lecture, I just used some examples to show the technique, but now this is one of the classic examples, and it will have this periodic orbit, which is also called a strange attractor, and this occurs in nonlinear systems. Like I say, it's an important case and with important solution. So this is the differential equation that we're going to use. There are many other, or several other anyway, nonlinear systems that will give a periodic orbit, but we're going to use this one for the example here. It doesn't look like it would give a periodic orbit, but it does. As in the previous chapter, we go through and try to find first the nullines and the equilibrium points. So the x nullines is a set of points where the first line in the system is 0. Okay, so here's the equation. Now we'll notice, in contrast to the previous cases in lecture 1, this is not a straight line. It's cubic. Okay, the y nullline is easier to draw anyway, and that's just the y-axis. It's x equals 0, because dy by dx equals minus x, so x equals 0 is the value of x that will send that to 0. These intersect only at the origin, so the origin is the only equilibrium point for this system. So to find out how the system behaves at its sole equilibrium point at the origin, we construct the Jacobian, and then we evaluate the Jacobian at 0, 0 and try to find the eigenvalues. So we have to work the eigenvalues through the equation. The trace of this matrix is 1 and the determinant is 1, and we end up with, when we solve this system, we end up with complex eigenvalues with positive real part. This is a spiral source. It's spiral because it has a non-zero real part for a complex eigenvalue, and because the real part's positive, it is a spiral source. So this is how the solutions, both in the linear and nonlinear system, are behaving near the origin. So here are the nullines in the phase plane. That's the y nullline along the wait a minute. Yeah, the y nullline at x equals 0, and here is that cubic x nullline So for once we have nullines that are not lines, or not, straight lines. Now from the Jacobian, we know that right near the origin, the solution is a spiral source. It's doing something like that. Well, what's it doing further from the origin? If you look out here, you might convince yourself that it's spiraling in. Okay, and we can look at more of the direction field, we will see that. So if we have something out here that's spiraling in, and something here that's spiraling out, what are they spiraling to? And that's where the periodic orbit comes in. We're just going to look at some solutions. Here is a solution starting near the origin, and it's spiraling out. Okay, but it looks like it's starting to come onto itself instead of continuing to spiral out. Okay, so one way to sort of check this, of course these are no proofs, you can do a lot more with these, but we're just going to do this much for this class. Okay, what I'm going to do next is I'm going to run the solution for a longer time and see if it doesn't move out into this region out here and start going towards infinity. It's a spiral source, so it should be moving out. So now I run the same thing, starting at the same initial point, and run it for a longer time, you see there's more cycles here because I've run this for a longer time, and I get about the same thing. It goes out to a certain point and then it seems to just sort of stop. And I can repeat that one more time. And here again, same initial point for quite a few more cycles, and we don't seem to be getting any further out towards infinity. It is spiraling out for a while. So now let's look at solutions that start further out from the origin and see where they end up. In this case, we started out here and we see it's coming in, but it's coming in, it doesn't go all the way to the origin. It's coming onto this orbit. This is the periodic orbit. You can kind of see how it's here. Remember, the solution curve here was moving out and it was ending up approaching asymptotically to that same orbit. We're going to try another initial point that's further out, and here's another one. Again, it starts out here and it seems to start moving in, but instead of moving all the way in towards the origin, it moves in until it gets to this orbit. This is the periodic orbit. It has another name called strange attractor. Of course, not all nonlinear systems that have a spiral source at the origin have periodic orbits. It just happens to be peculiar to this case. What does it mean that it has a periodic orbit? What's going on with these? Well, the idea is that if it starts here, a certain amount of, if you want to kind of make some general physical ideas towards it, a certain amount of energy seems to be added to the system as it's moving until it gets to a certain point out to here. The system that starts here loses energy, and so it's coming into the system. Now, I couldn't get a solution, a composite solution for the system that I had before, so I'm using a phase portrait for a similar nonlinear system showing a periodic orbit. This periodic orbit is in green here. Right here, there's a periodic orbit. Solutions that start out here approach it in extremely nonlinear fashion, right? And the solutions that start inside the periodic orbit are spiraling out towards it. Now, this is, I said, a classic example of a strange attractor or periodic orbit in a nonlinear system, and the equations are all tend to be classified under the heading of van der Pol, in honor of the first person who observed them and studied them. Okay, what kind of system gives this? Well, van der Pol was studying electrical circuits, and he was using some resistors that were nonlinear. There's something called a tunnel diode. If you don't have to know this, I'm just trying to explain it, what's going on here. And in a tunnel diode, if you have a resistor, if I have so what I'm trying to show you is this tunnel diode characteristics. Again, you don't have to know this, it's just trying to explain it. If you remember the RLC circuit, resistance was some positive value, V equals IR. You could write an equation like that, and here would be the resistance, would pretty much be the slope of this curve. Well, in a tunnel diode, you'll have a region where it's a positive slope and then a region where it turns over and it's negative. So now you have negative resistance. That's a kind of behavior. This is a quantum effect in the tunnel diode, and it's but this is the kind of behavior, the kind of characteristics that give rise to something that looks like this. So you see it in electrical circuits with a tunnel diode. Also, by using this tunnel diode model for nerve conduction, there's a famous study of conduction in the squid axon They use a squid axon because it's big and they can put electrodes in it. And I'll show you how that looks too. So it's a little more complicated than what we have here, but I want you to remember when we look at this that we had a simple form here, but we had this cubic, and then we had a straight line solution here, and we had a cubic. And so you're going to see that again. So what I'm trying to show you is that these models have great importance in science, in physics, in engineering, and even medicine, beyond just examples for this class. And this is a classic example, which is why I'm just going over it. So here is a demonstration running in real time, so to speak. It's from Scholarpedia, and we're talking about the Fitzhugh model, Fitzhugh-Nagumo model for axon conduction. And now look what we have here. Look at this line right through here. It's coming down through here, it's going up and over here. This is the cubic. That was that cubic nucline. And previously we had a nucline that was a y-axis, so it was a vertical line, but in this case we have one with a diagonal. So here's the other nucline. Again, I didn't draw very well, but that's not surprising. So you can see right here nucline just like we studied a few minutes ago. So let me take those off. You can see those. And now what this is showing is orbits, how these orbits are excited. Out here is oh well, let's do it twice. Okay. You'll see when there's a strong enough stimulus, then the axon will fire, will depolarize and fire. So this is a weak stimulus coming in here, and you'll see it's going to be right along this first curve. It'll be turning red in a minute, I think. I guess it quit running. Okay. I can't write on it at this time, that's why. Okay, weak stimulus, you're getting some of these orbits right down there, just these curves, these solution curves down there. And then you get up to where there's a strong enough stimulus, and then you get that orbit, that outer orbit right here, which now we won't be able to see it running because I'm writing on it. This outer orbit that's coming along here, this is your strange attractor. This is your limit cycle or periodic orbit for this case. So you can look that up if you're interested. A lot of opportunity for research here. So let's go back to the lecture a little bit and talk about some of the vocabulary. So this periodic orbit that arises from as a limit of other solution curves in the nonlinear system is called a limit cycle. Do they violate uniqueness? No, because the curve isn't crossing itself, or it's not being crossed. It's going over itself, but it's not at the same point at exactly the same time. So in a sense it doesn't cross. If you were to stretch this out in time, you'd see it's not crossing. Okay, so it's called a limit cycle, does not violate uniqueness. Now if it's stable, it's called an attractor. There could be limit cycles that aren't stable. It could be semi-stable or not stable, unstable, but the stable one is called an attractor. So here's that stable one called an attractor, and that makes sense because nearby solutions are approaching it in forward time. So that sort of makes sense. Now why is it called a strange attractor? It's called a strange attractor because the geometric shape of it is very strange. You notice those previous examples. Here we have this periodic orbit. Previously we'd see circles or ellipses, some nice shape like this, and now we see orbits that are neither circular nor elliptical. So they have a strange shape, so they get called a strange attractor. So again, if you have an interest in this, you can look up the van der Pol equation or related solutions for the van der Pol equation or model.